In this lab, we were asked to observe and analyse the motion of an object dropped from rest. For this experiment, the motion was filmed and the footage analysed to extract the object's position information over a short time period. A computational model was constructed to see how this would compare with the observed motion. In constructing the computational model, we applied Newton's second law in the update form to obtain the position data, and we also applied Newton's second law in the F equals mass times acceleration form. So here is part of my computer code showing G equals 9.8 meters per second squared, and also the assignment statement for the weight force on the system. This is the video of my object falling, and it shows that you can see that I used a summer shoe and it had mass 200 grams. The time of the fall was actually 0.734 seconds as measured by tracker. To construct the computer model with drag, the changes I made to the previously mentioned model were that I took Fnet equals the weight force plus the drag force, and we were told to use this model for the drag force, minus A being the coefficient of drag, minus to show the direction, multiplied by the speed squared. To find A, I followed the suggested procedure of comparing the predicted final position calculated by VPython with the observed final position from tracker, and I found that a value of A equals 0.0001 made for a close match of values. Here is the graph then of the three things, the two models and experimental data. The plot of my tracker data has a slight kink at the end, which is due to human error. This was due to my trying to compensate for my belief that the last frame of my footage was actually not depicting the shoe in motion. This is the video again, and as you can see, there's a thud and pause right at the tail end of that fall there. I think that my data from tracker is flawed as a whole, actually, because I took my calibration measurement from this corner just there to the ground, and that was 2.09 meters. Unfortunately, because of camera distortion, the distance of the fall depicted is actually farther than in reality. The tracker measured a fall of 2.32 meters. And my computer model actually has my object falling 2.35 meters, which is yet another discrepancy then in my data. Putting all this together, the difference between my experimental data and model without drag could perhaps be explained by the effect of drag, except that my with drag predictive model actually showed a negligible drag effect over the 2 or so meters of drop, and this is shown with these visualization windows. If drag was present, I would expect it to pop up here as a different colored arrow. So my data appears to show, my data is currently graphed, appears to show negligible drag force. Thinking about the velocity versus time predicted by my models, I would say that this currently graphed this current graph does not predict a terminal velocity. Terminal velocity would be where the frictional force of air resistance equals the weight of the object, thus resulting in a net force of 0, and so the object falls with a constant terminal velocity. However, I then ran my model with drag for a time to 10 seconds, and this is what I got. So this was the time when it would have taken my shoe to fall around 490 meters. By eye, from about 8 seconds, we have a straight line graph indicating constant speed of the falling object. If the object had been initially thrown downward instead of dropped from rest, the computer model I then ran resulted in the following position versus time graph. By eye, it can perhaps be detected that terminal velocity is reached slightly earlier than 8 seconds for the thrown object, shown by the blue line, as compared with the object which starts from rest, the red line. Extrapolating to a graph of velocity versus time, we have the following. So the straight line at the top is the terminal velocity position, and what I would say is, predicting from the position versus time graph just shown, the thrown object would show a steeper curve. These then are my findings. Thanks for watching.